Thanks, and I'd like to thank the organizers also for introducing me and for inviting me to give this talk. It's a great pleasure to be here. Okay, so the subject is it's about homological mirror symmetry for complements of an anti-canonical divisor inside toric Calabi-Yau, and this is something I will describe in detail in just a minute. So this is like the main subject. So it's homological mirror symmetry in yet another setting, but it's also the goal is also like to give to hint to general ideas of how to about the connection between SYZ mirror symmetry and homological mirror symmetry, and of these to wrapped Floer theory, and how these things work on open manifolds where we do not assume any kind of exactness at infinity. Okay, so the setup first. So we start with a toric Calabi-Yau. So M would be a toric variety with a first Chern class equal to 0. That's a toric Calabi-Yau, and perhaps additional something which comes from symplectic reduction. So maybe some completeness assumption. And okay, so examples to keep in mind. So you can keep I will work of dimension 3, though it's not strictly necessary. And the examples, so for most of this talk, just thinking about C3 is good enough. So another example would be the O-1 plus O-1 over P1, the canonical bundle over P2, and such further examples. What? Yeah. Now, yeah, so we start with this manifold. Now, these manifolds themselves, one can show, I think it's a result by Ritter, the Fukaya category of these is trivial. But we want to remove an anti-canonical divisor. Okay, so this works as follows. So each of these manifolds, so M is obtained by reduction, by symplectic reduction. So we're talking about the dimension 3, so it's some kind of n-dimensional torus, which sits inside the standard. So we're the standard torus acting on Cn plus 3. So just by the standard action, which is just multiplication, diagonal multiplication. So this torus sits inside, preserving. So this one preserves the holomorphic volume form, or in other words, the product of all the coordinates. That's a required when you do symplectic reduction by a torus like this on Cn, you obtain something which satisfies that the Chern number is 0, and these are the manifolds under consideration, and okay, so it follows that there is a global holomorphic function on M namely the product of all coordinates. So this is some kind of, we did some kind of quotient, but still we have that, we can take the product. Okay, and by the way, just because of this assumption, one can show that these manifolds are not compact. That's just okay. So let me draw a picture. The manifolds we will be considering will be for which we will actually discuss homological mirror symmetry. Will be we take this manifold M and we remove an anti-canonical divisor, say f, the pre-image say of 1 or any constant under this function. So let's draw a picture. Any questions? Okay, so the picture. So the picture will be as follows. So I'm going to consider. So there's a function from x to r times s1, which will be given so this function f, which we have here, is a function to c minus the 0.1. I'm turning it into a function to the cylinder. Okay, and the picture is as follows. So this is our cylinder, and let's call this function pi. Okay, and so the general fiber the generic fiber of this for a generic point, the pre-image of this function will be a copy of c star squared. So it's and we can think of this c star squared as foliated by Lagrangian tori, which in a minute I will describe. Okay, so we have something with a cylinder, and over the cylinder we have these c star squareds, and so this is the general fiber, and then there is a singular fiber, which I draw something like this, and the singular fiber corresponds to the points just to the singular points of f, which is singular points is when you get two coordinates are 0. So the singular fiber is when the product of the coordinates is 0, which is the union, basically the union of toric divisors. So for C3, let's just draw. So all the geometry of our toric variety is encoded in this singular fiber, which so for these examples. For each example, there's some kind of diagram which is embedded inside R2, and which describes the structure of this singular fiber. Okay, so now just one more point about the geometry. So since we have a toric variety, we have so when we started with it, we had a toric variety. So we had a torus. There was a residual torus. So there's some kind of 3 torus, which is the quotient of the 2 tori up there acting. So now, since we've removed something, we have destroyed part of the symmetry, but we still have an action here. So we have a 2 torus acting on this, preserving the fibers, preserving pi. So it's a Hamiltonian action. So it preserves pi and the volume form. Well, let's take 1 minus f. So omega is the so omega, there's also like the fact that the Chern class is 0 means that there is some Calabi-Yau form which descends from the volume form on Cn, since we are preserving the product of coordinates. And actually, but now after we remove this fiber, we switch to some new volume form. We won't be talking much about this. It's just something which is, when you want to talk about SYZ and things like that, you have to mention what is the volume form you're talking about. So I'm introducing it now. So geometrically, what we have here is this picture where we have so basically a fibration over a cylinder, and we have this. So each fiber is itself foliated by toric orbits, except for the singular fiber where some things degenerate. Okay, so this manifold carries a SYZ fibration, by which a special Lagrangian fibration, which I think Gross is responsible for, and a special Lagrangian 3 torus fibration, you can, in this picture you can see these Lagrangian tori. It's just, well, you take some torus. So for a given fiber here, you take some torus, and then you parallel transport it around a circle. Then you get you get this Lagrangian torus fibration, which degenerates in some at this, where we get the degenerate tori in this singular fiber. So this is okay. So this is the standard setup for SYZ mirror symmetry, and in fact, so this subject of toric Calabi-Yau, it's been studied from the it was studied by physicists in connection with mirror symmetry, and then there is a paper by Yau and collaborators showing that somehow ideas from mirror symmetry can be applied to the open setting, and he used mirror symmetry ideas to compute Gromov-Witten invariants. But from the point of SYZ, there was so I'll just mention, yes. Yeah, it's there's like it's pinched. Well, there's like the generic one would be some pinched. I think something like this times an S1. That's it's the simplest type of singularity possible. Okay, so like this is when you, in the case of C3, this is like the model of the simple, like in books in the text on SYZ. That's like it's called it, like it's a focus singularity. It's somehow the simplest there is. Okay, so yeah, so there is I should mention Aru, Abu Zaid, and Zarkov. So this is one group, and then independently another group, Chan, Lau, Leung, I think both in 2012, I'm not exactly. So they computed, so when we have a special Lagrangian fibration, there is a notion of an SYZ mirror, where, which is some kind of space whose points are tori in this fibration and local systems. I will have more to say about this a little bit later. For now, I'll just write down. So what these did, they showed that the SYZ, so they constructed the SYZ mirror, X check, which as a set we should think of as Lagrangians, as pairs of Lagrangians and formal local systems. So these are so we have these Lagrangians, which basically the ones I described here, and then the local systems, which you can think of as just the first cohomology of L B with fibers in with values in some how should I describe this? With some module of, so I'll just write it here. So lambda star is I would say it's the submodule of the Novikov ring, where the valuation is greater than 0. So yeah, this is just formal nonsense. I mean, best think of this as just, I mean, a posteriori we may think of this as just as values in just the cohomology with values in S1, just local systems. So this is just something formal, as long as we don't know things about convergence. But yeah, at this level. So yeah, so what they did is they took this set and they gave it the structure of a rigid analytic manifold, or if you want, just a complex manifold, which they wrote down as so they gave an explicit description with as yes, each yeah, that's how you get, like, it should be a three complex dimensional manifold. I should think of, oh, I didn't obey the rule. So you should think of as a real and imaginary part. The real part is the Lagrangian, and the imaginary part is the or no, more precisely, the phase and the, like, it's a complex number, so it has a phase and like an argument and a absolute value. So the absolute value is somehow the Lagrangian, and the phase is the the local system. So in any case, they wrote down a, so they constructed it and they came up with this. So it's, let's write it like this. So it's, I'll write it like this, x, y, u, v. So it's a subset in k squared, k star squared, which you can think of as C or some Novikov thing, doesn't matter. So it's a subset where the first two are in C, the second two variables are in C star squared, and which satisfy an equation of the form x times y equals f of u and v, where f is some Laurent polynomial which can be described in terms of the toric diagram. So it's some relatively rather explicit Laurent polynomial, which I won't write down, but so we can really tell what monomials appear in that Laurent polynomial, but then like it's not completely it's at least in this work, in the work that I mentioned, it's not completely what the constants there are, but the techniques of mirror symmetry should allow even to tell also what are the constants. Okay, so this is this is the geometric setup. So we have this symplectic manifold. It has a special Lagrangian torus vibration, and it has an SYZ mirror. So I want to discuss it from the point of view of homological mirror symmetry. So I'll state a few theorems. So if we want to do homological mirror symmetry, we have to make sense. Like a homological mirror symmetry means there's an equivalence between the category of coherent sheaves, derived category of coherent sheaves on one side, and some version of the Fukaya category on the other side. Now, when we work with open manifolds, we need the symplectic side is the wrapped Fukaya category, but at least when we're not working with exact manifolds, we have to first define what we mean by the wrapped Fukaya category, and then we can proceed. So the goal is, what I will do is I will state a few theorems as if these things are already defined, and then I'll spend the rest of the talk to make sense. So like, let me write it down. Goal. The goal would be to make sense of the wrapped Fukaya category of our manifold X. And specifically, I would like to define things like symplectic homology of X. Maybe it should be relative to this. So there's this Lagrangian torus vibration. So maybe it should have as a parameter. I mean, it's not going to be an invariant of X. It's going to be an invariant of X together with the data of this Lagrangian torus vibration. So I would like to define things like symplectic homology, and for favorable Lagrangians, I would like to define what is wrapped. What is the notation? I think this is the wrapped intersection Floer homology. Say we have two Lagrangians, and suppose we can overcome issues about obstructions and so on. So I would like to say what I mean by wrapped foci by these objects. But for now, so I'm going to pretend that I already did that. So I just want to formulate two theorems. Which is at this point work like it's not yet published. So so one theorem is regarding the zeroth symplectic homology. It's just a statement about zero symplectic homology, and the statement is that it's equal to basically the algebra of functions on this SYZ mirror. The zero symplectic homology. So the way I've stated it, so I just want to just so it's independent. So like I stated it as if you do this SYZ construction and then out comes X check and then this is symplectic homology. But the proof is it's not. It doesn't. I just wrote it this way because it's shorter. So independent of SYZ construction. Okay, so in a minute you'll see what's the relevance of this to homological mirror symmetry. Yes. Oh, I think I did. Right. So from after I'll state the second theorem, it will be clear that from general nonsense about it should be this kind of result should be expected. Or maybe I should have left at least a picture there. So okay. And then the second theorem is okay. So let me just redraw that picture. So this is the picture of our manifold. So so now we have this this Lagrangian torus fibration. So we can choose a section basically we pick some kind of line along this along the base of this fibration, and then we pick some Lagrangian section for this like the fibers itself foliated by Lagrangian tori. So I pick a Lagrangian section for this fiber, and then I parallel transport along this. I get a Lagrangian section, and if I'm careful to not go through. So there's this singular fiber. So I should be careful that when I hit this singular Lagrangian, I don't this line doesn't go through that singular fiber. So if so a Lagrangian section sigma, if chosen carefully, is tautologically unobstructed, by which I mean there are no holomorphic disks, which you can just let's fix this standard complex structure, which we obtain from just there's a standard symplectic structure when you do the symplectic reduction, because it's equivalent to some kind of GIT quotient. So if we use that one, there will be no disks. You can just apply a maximum principle, because you have this holomorphic map. This map which here is holomorphic. So a disk, any disk has to remain within the fiber just by maximum principles, and therefore the only ones which will ever occur will be in this singular fiber. So if you don't hit the singular fiber, there are no disks, and so it has well-defined Floer homology. Okay, so that's just, so I claim, so that would be, let's call it first part. The second part would be that, okay, there is an open-closed map, a closed-open map, which goes from the zero symplectic homology to the wrapped Floer homology of this section, which I called sigma. And it's an isomorphism. And 3, so there's Abu Zaid's generation criterion, which says that there's, if we take the, I think it's the nth Hochschild homology of this Lagrangian, there's some kind of construction which we can carry out. So if we take this thing, then there's a map from this to again to zeroth symplectic homology, and it hits the unit. And all this, well, okay, so that's just some kind of statement, and you may ask why I care, but this is Abu Zaid's generation criterion. So like all these, you may not be interested in any of these statements, but taken together, so by Abu Zaid's generation criterion, these statements taken together, they imply that if we take the wrapped Fukaya category, or some kind of derived version of this, then this is equivalent to the category of coherent sheaves on this SYZ mirror, which in this case is just an affine variety, so it's the same thing as finally generated modules over this SH0. So taken together, all these statements give us a quite explicit description of the Fukaya category, and in particular, they give us homological mirror symmetry. Okay. So any questions? Okay, so maybe I'll just rewrite the last line because so the end result of the discussion was this that the derived Fukaya category of X, when it's wrapped with respect to this Lagrangian torus vibration, it's equivalent to okay, so let's so now I'll try to make sense, like what is the how we define the wrapped category and what kind of ideas go into these statements. Okay, so any questions so far? Okay, so yeah, so to give an idea of how this works, it's best to have in mind I give a brief review of a toy model. Which is just the case when we take T star S1. So the cotangent model of S1. So first of all, this has a special Lagrangian fibration given just by these tori. And then, so let's call this X. And then X check is, so let's call this the base of the fibration. So X check is the set of, as a set, it's the set of pairs of these Lagrangians where B is any point in this base of the fibration, and local systems so a local system is just an element of with values in S1, H1, sorry. Okay, so this is the description as a set, and it has coordinates. So if you put these defined coordinates, which identify it with C star squared. So as a complex manifold, it's C star squared. Now, okay, so first, and then how do we describe the wrapped Fukaya category? So the thing is that so the first object in the wrapped Fukaya category is symplectic homology. And if I want to talk just about zero symplectic homology, what I do is I look at, so I take a Hamiltonian, which is convex and depends convexly on this coordinate S, which goes in this direction. And it's near infinity has, so it's just a function h equals h of some function of this variable s, and it's the derivative is constant near infinity. So I pick I take such a Hamiltonian. So for such a Hamiltonian, if I want to understand the Hamiltonian flow, so basically what we have is that this h goes from 0 to from 0 to plus minus this constant near infinity. So this h prime goes through certain whenever it hits an integer value, we get a periodic orbit. That's the way the flow of such a Hamiltonian is described. Yes. So for each integer we get a periodic orbit. So and then so symplectic homology is defined as follows. So let's call it zero symplectic homology of x is the limit, the direct limit as a goes to infinity of Floer homologies of, say, a times this function h, and there is some notion. So when we increase the slope, we get periodic orbits which correspond to higher and higher windings around, and then so as a module, this is equal to just so let's work with coefficients in C. So as a module, this is so actually as a module and as a ring, it's equal to the algebra of Laurent polynomials. So how does this work? So basically we get each time this h hits an integer, we get so if it hits the integer I, we get something which corresponds to x to the power of I. So as we go through all the integers, we get x plus minus I, and then the product is just xi xj. This is some, well, it follows from, I think this is Viterbo's theorem. Okay, so we get the algebra of Laurent polynomials, and we see that it is indeed it's the algebra of functions on this mirror. And yeah, the only thing I want you to take away from this is that somehow that symplectic homology is something which comes from taking a direct limit where you do higher and higher slopes. And these slopes correspond to taking periodic orbits which wind around more and more times. And a periodic orbit which winds around n times is roughly a function, gives roughly a monomial x to the power of I. That's what I want you to take away from. Is yeah, x to the minus. Yeah. So this means like the Hamiltonian flow of this. So on this side, you will be going around like this, and on this side you will be going around like this. Okay. So I guess that's okay. That would be enough. So this is some kind of picture, and you can also have so a Lagrangian section would just be some kind of line here, and the same. So this same computation will apply to, you will get the same answer if you take so let's call this section sigma, and what was the notation for it? So if you take the 0th Floer intersection Floer homology for this sigma, you will get the same answer. And like having a Lagrangian section which has its Floer, which with Floer homology is somehow concentrated in degree 0, that is equivalent to having to the mirror being affine. And so when the mirror is an affine manifold, you expect this kind of relation between the 0th symplectic homology and the 0th wrap Floer homology of this Lagrangian section. This is like general nonsense, but I don't have time to explain. 1 second, it's just like this general nonsense is due to gross keel hacking. Okay.
So the equalities here are they the same as the photo from that above?
Yes, yeah. So there's this general, yeah. So this is the general picture. So now I just want, okay. So this is when we're looking at. So this is the toy model. I want to adapt this toy model to the more complicated picture which we have of the Lagrangian torus vibration with singularities. So I just want to say, let's see, I'm 15 minutes. Yeah, I think I'll have time to explain this point. So yeah, so the question is when we are dealing, so how do we do this more generally when we have like a Lagrangian torus vibration with singularities? But first we must address a certain issue, which is how do we, so before we, so there's an issue that Floer homology may not be well defined when you work on an open manifold. Okay, so I want to be very brief about this. Okay, so defining Floer homology on open manifolds. So Floer homology is defined by there is some kind of where we count we have some kind of Floer differential where we count certain Floer trajectories, but there is an issue that when you're on an open manifold, you don't have compact results, so you might have some kind of divergence. Now this issue, so there are two issues which might arise. One is where you have kind of a divergence, where so I would like to imagine that when you have a divergence, it's like converging to some singular kind of object. So schematically, you might have that you have some kind of sequence, and in the limit, it has a certain singularity, which occurs at some point. So let's call this a type 1 divergence. And then there's a second type of divergence, which occurs when you have a sequence, and in the limit you get something where somehow an entire loop, a sequence of loops, it converges to infinity. So you get some kind of breaking at infinity. So it doesn't occur at some point. We have some breaking at infinity. So this I call type 2. Now this one, the type 1, is something which can be ruled out. So we need to limit. So if we want, so usually when we want to define, we want to set up a Floer theory, we have to somehow impose restrictions on our Floer data. So to deal with this, we just need to require a Floer homology somehow receives as a parameter a Hamiltonian and an almost complex structure, and then we require that these two things they have bounded geometry, which I don't have time to explain, but it's some kind of straightforward condition. So let me write. Call it not bounded, but something which I call I bounded. So that's some kind of requirement on the behavior of the Hamiltonian, the almost complex structure, and all kinds of derivatives associated with it. And it's something which you can verify when given a particular Floer datum, does it satisfy it or not? So we can impose this, but the point is not just to find some kind of condition, but is it some kind of condition which one can work with? So usually in Floer homology, you want some type of contractibility. So this condition has the property. So that's a theorem which is published in my paper. So if H1 is less than equal to H2 and H1 J1 H2 J2 have this satisfy this condition of I bounded geometry, then there is a monotone homotopy which goes from one to the other. And this is the kind of result you need to show independence of particular choices. So what I'm saying is that I-bounded geometry is a sufficiently weak condition to allow this kind of existence of homotopies under just this monotonicity condition. So it's weak enough for that, but it's strong enough to rule out this kind of divergence. Okay, so that's how I deal with this. Now, now type 2 condition. This is something which somehow is directly related to the definition of wrapping. So the way to rule this out. So suppose you have some kind of Hamiltonian flow where the distance, so outside of a compact set, the distance of the Hamiltonian flow of a point, the distance of a point after it has flown a little while, after it has flown the time one flow of this Hamiltonian from its starting point is greater than some constant, which is at least 0, then you cannot have this type of divergence. Yeah, if this is true for all p outside a compact set. So plus, say, additional boundedness assumptions. This is something which is not hard to prove. Then there is no type 2 divergence. Okay. Now the point of this. So this is the really important point about defining rapid Floer homology. So this condition is somehow also natural in our definition of wrapping. So the thing is that usually it's difficult to figure out, like you have a Hamiltonian, you want to figure out something about its Hamiltonian flow, then that's like, usually it's difficult to figure out. But when you work with Lagrangian torus fibrations, so you have like an SYZ fibration. This is so you really understand the flow, and then so it's easy to achieve for a specific type of Hamiltonians. So let me write this down, and I'm almost done. So I'll just have time to explain this point, like what is wrapping. So yeah, it will take me 5 minutes, I hope. Last condition is easy to satisfy for if, say we have some function h, let's call it g. So a function g from x check to, in our setting, we're actually like, let's not be very specific. So yeah, so we have some function. So g is a Lagrangian torus fibration to some base. And h is a function from x check, from b, so h to r, such that, and so it's easy to, and now we want to do Floer homology for the function h composed with g. So we have this Lagrangian torus fibration that goes to a base, and then we have a function to the base. Then it's easy to satisfy if the gradient of this function h j, let me put it in, so no, not like that. So let's write it like this, such that H is Lipschitz with respect to action angle coordinates. Because so like there is this when you have a Lagrangian torus vibration, there is something called action angle coordinates, which locally away from singularities makes your picture look exactly like you're living inside the cotangent bundle of some n torus, and then this function h, its Hamiltonian flow is just like moving you around on certain tori, on these, like it's just like a higher dimensional example of this picture we had before with the cylinder, and there's like natural there's a natural coordinates. So it makes sense to talk about being Lipschitz, like natural coordinates on the base. So it makes sense to talk about being Lipschitz. And the point of this thing, this restriction of being Lipschitz, essentially it's similar to the construction, this restriction when we have a cylinder, and I'm asking something to be linear. So linear means that it does not. So if I say that it's linear near infinity, it means that the flow winds around. So it winds around a number of times, and then at near infinity, if it's say it's linear and it's equal to some constant which is not an integer, then what the flow does, it winds you around, but you get back like a fixed distance from where you started. So when you impose this condition of having these Lipschitz functions, you can easily find a subset which is cofinal in the set of all these Lipschitz functions, which satisfies this condition. So I just write down. So for example, so the symplectic homology of x with respect to the Lagrangian torus variation would be the direct limit over these, let's call them just Lipschitz functions, where Lipschitz is meant with respect to these action angle coordinates. So I will take a direct limit over such Hamiltonians, and this will reconstruct. So this is the definition of symplectic homology, and and the definition for wrapped Floer homology of a Lagrangian will be similarly defined using Hamiltonians which satisfy this Lipschitz condition. And once I define wrapping in this way, I can state at least, and with this I will finish. So the bottom line is that homological mirror symmetry. So I don't want to make too precise a statement, so I'll just say, so it relates this kind of wrapped Floer homology, wrapped Foucault category, which is defined in this way using these Lipschitz Hamiltonians with the bounded derived category of coherent sheaves on with coherent sheaves on the mirror. Okay, so with this I think I'll finish.